Let us discuss chemical equilibrium. In chemical equilibrium, we will take a sum 1 mole of N2, 1 mole of N2, and 3 moles of PCl5, and 3 moles of PCl5, are placed in a 100-liter vessel, heated to 227 degrees Celsius, The equilibrium pressure is 2.05 atmosphere. 2.05 atmosphere. Assuming ideal behavior. Calculate degree of dissociation of PCl5. And Kp for PCl5 gives PCl3 and Cl2. Okay. So now, as per the sum, what we have taken in the sense 1 mole of N2 we have taken and 3 moles of PCl5 we are taking in a 100-liter vessel. Okay. So what happens means this PCl5 undergoes a decomposition. That PCl5 undergoes a decomposition to give PCl3 and Cl2. This N2 does not react with any one of these substances. N2 does not react with any one of these substances under the given condition. Okay. Initially, how much PCl5 we have taken? That is 3 moles. It is undergoing dissociation. Therefore, how much will dissociate? Will it dissociate completely or partial? That is there. So now PCl5 dissociating completely or partially. How do we know it? Nothing idea is given. Whether it is dissociating partially or completely, nothing idea is given. We will assume that, anyhow it is dissociating. How much we do not know. Therefore, we will take X moles. Okay. So at equilibrium, how much is there? Means 3 minus X moles is there. PCl3 X moles produced, Cl2 X moles produced. Okay. Now what we have to find in the sense, we have to find alpha. For this. Okay. What are the other data given? Equilibrium pressure is given. Equilibrium temperature is given. Volume of vessel given. So if we assume ideal gas, then we can take PV is equal to nRT we can take. So P is called equilibrium pressure, we will take. P is called equilibrium pressure. V is called volume of vessel, we will take. N is called total number of moles at equilibrium. N is called total number of moles at equilibrium. That means 3 minus X plus X plus X. Therefore, we can say 3 plus X moles. So we can say 3 plus X moles. We can say 3 plus X moles. Then capital R is called universal gas constant. That universal gas constant is 0.0821 liter atmosphere per Kelvin per mole. Then temperature is given 227 degrees Celsius. That means 500 Kelvin. Temperature given 227 degrees Celsius. That we are converting into Kelvin. How much in the sense? 500 Kelvin we can say. Okay. By simplifying this, we can get X. We are getting X. We are getting, sir. Before simplifying this one, let us check the substituted things are correct or wrong. We will check it. Here we have substituted number of moles, total number of moles. How much in the sense? 3 plus X moles we have substituted. Why we have substituted 3 plus x means this 3 minus x plus x plus x, therefore 3 plus x moles we have substituted. Total number of moles at equilibrium we have substituted here. And how much pressure we have substituted in the sense 2.05 atmosphere. This 2.05 atmosphere is the equilibrium pressure. Equilibrium pressure means what? At equilibrium, PCl5 3 minus x moles present, PCl3 x moles present, Cl2 x moles present. And see the initially what and all you have taken in the vessel, you see. PCl5 3 moles we have taken and N2 1 mole we have taken. This N2 does not react with any one of these substances. At equilibrium, this N2 will be present or not? This N2 will be present, no? This N2 also will exert pressure, no? Therefore, this 2.05 pressure is exerted by which one? Part is Cl2, part is PCl3, part is PCl5 and part is N2. Therefore, we have substituted here 2.05 atmosphere. 2.05 atmosphere we have substituted in the sense we have included N2 pressure also. 2.05 we have substituted in the sense we have included N2 pressure also. Therefore, in the total number of moles, we have to include this N2 also we have to include. Therefore, instead of 3, we will write now 4 we will write. We have written 4. Why we have written 4? This N2 number of moles also we have included. Otherwise, if you want to write 3 plus x, what you have to do means N2 exerting how much pressure, that pressure you subtract from this, then you substitute the value. Okay. If you do not do, if you substitute 2.05 directly, then you are including N2 pressure also, nitrogen pressure also you are including. Then include number of moles of nitrogen here. Okay. Sir, now it is correct. Okay. Now we will simplify this one. We will get x. X is how much in the sense 0.9939. 0.9939. Okay, we got x. X is called what? Number of moles of PCl5 dissociated. Number of moles of PCl5 dissociated we got. Now they are asking us to find a degree of dissociation. So degree of dissociation is equal to moles of PCl5 dissociated by initial moles of PCl5. Okay, alpha is called degree of dissociation of PCl5. X is called moles of PCl5 dissociated. 3 is called moles of PCl5 taken initially. This ratio is called degree of dissociation. Now we will substitute number of moles of PCl5 dissociated, we will substitute. Okay, initial number of moles of PCl5 we have written. We are simplifying, we are getting degree of dissociation so and so value. Okay, we got degree of dissociation. Next, what we have to find? Kp we have to find. Okay, they are asking us to find Kp. Okay, so Kp is called what? We will see. This Kp is equal to, what is the formula in the sense? Kp is equal to partial pressure of PCl3, partial pressure of Cl2 by partial pressure of PCl5. It is Kp, which is equal to partial pressure of PCl3. We can write it as mole fraction of PCl3 into total pressure. Partial pressure of Cl2, we will write it as mole fraction of Cl2 into total pressure. Partial pressure of PCl5, we will write mole fraction of PCl5 into total pressure. Now, for mole fraction of PCl3, we will write it as number of moles of PCl3 by total number of moles, total pressure. Mole fraction of Cl2, we will write it as number of moles of Cl2 by total number of moles. Mole fraction of PCl5, we will write it as number of moles of PCl5 by total number of moles. Then we will write a number of moles of PCl3, number of moles of Cl2, total pressure by number of moles of PCl5 into total number of moles. Okay, we have written. Now we will substitute the values in order to get Kp. So Kp is equal to number of moles of PCl3. How much? X. PCl3 number of moles X. Cl2 number of moles X. PCl5 number of moles 3 minus X. Okay. X we have calculated as 0.9939. That we will substitute. So PCl3 number of moles 0.9939. Cl2 number of moles 0.9939. Here total pressure is there, that we have to substitute. Okay. Then PCl5 number of moles 3 minus x, x is 0.9939. Okay. Then here n is called total number of moles. So now we have to substitute this n, total number of moles we have to substitute. This P is called equilibrium pressure, we have to substitute. Okay. Those two if we substitute, we will get Kp. Okay. Now equilibrium pressure, how much shall we substitute? Total pressure, how much shall we substitute? Shall we substitute 2.05? If we substitute 2.05, then we have to include N2. We have to include N2. If we substitute 2.05 atmosphere as the total pressure, otherwise equilibrium pressure. Okay. Equilibrium mixture pressure is 2.05 atmosphere. If we substitute, then you have to include 1 mole of N2. Because this N2 is exerting pressure that is included here. If you don't want to take 1 mole of N2, in the total number of moles, if you don't want to include 1 mole of N2, then subtract this corresponding pressure here. Okay. Otherwise, do it one thing. If you want, you substitute 2.05 directly. 2.05 atmosphere, you substitute it. This P is called total pressure. Otherwise, pressure of equilibrium mixture, you substitute as 2.05. That means we have included N2. Okay. In the total number of moles, include N2. That's all. In the total number of moles, include N2. Okay. Sir, total number of moles, how much in the sense? We already said 4 plus x. 4 plus x is called total number of moles. X is 0.9939, that you substitute. Okay. Therefore, total number of moles is 4.9939. It is total number of moles. Okay. So now we have included N2. Here also we have included N2. Therefore, no change in the value. So this on simplification we are getting Kp. Therefore, Kp is how much in the sense 0.2. We got a Kp value. We got equilibrium constant value. We got it. Let us go to next sum. The next sum is ammonia is heated at 15 atmosphere. Ammonia is heated at 15 atmosphere from 27 degrees Celsius to 347 degrees Celsius. Assuming volume constant. Assuming volume constant. The new pressure becomes 50 atmosphere. The new pressure becomes 50 atmosphere at equilibrium of the reaction 2NH3 gives N2 plus 3H2. N2 plus 3H2. Calculate percentage of mole of NH3. Percentage of mole of NH3. Percentage of mole of NH3 actually decomposed. Actually decomposed. Okay. So now in this sum, what we are taking initially, that you see, we are taking ammonia at 15 atmosphere, we are taking at 27 degrees Celsius, we are taking. Okay. Then this ammonia is heated to 347 degrees Celsius. Volume is kept constant in this process. The new pressure becomes 50 atmosphere at equilibrium. The new pressure becomes 50 atmosphere at equilibrium. That means what? Equilibrium means ammonia is decomposed. So ammonia is decomposed at which temperature? Ammonia is decomposed at which temperature? At 27 degrees Celsius or 347 degrees Celsius? What we have to take? Here at 27 degrees Celsius we have taken ammonia. That pressure is 15 atmosphere. At 27 degrees Celsius, ammonia is in equilibrium or what? Now in the laboratory, liquor ammonia we are using. Liquor ammonia in the sense concentrated ammonia we are using. And even ammonium hydroxide solution we are using for salt analysis. So we are using ammonia in the laboratory in the sense at laboratory temperature, you know that around 25 degrees Celsius. Therefore, we are using in the sense ammonia is stable at that temperature, isn't it? Therefore, at 27 degrees Celsius, we can say ammonia is not decomposed. Okay. So ammonia is not decomposed in the sense at 27 degrees Celsius, ammonia is at ammonia only. Okay. So we are taking ammonia at 27 degrees Celsius, ammonia is there. That ammonia is exerting 15 atmosphere. Okay, sir. So we are taking initially what in the sense, initially ammonia we are taking, that pressure is the pressure of ammonia is how much in the sense 15 atmosphere. Then it is at the temperature of ammonia is how much in the sense 27 degrees Celsius, converting into Kelvin in the sense 300 Kelvin. Okay, converting into Kelvin in the sense 300 Kelvin we can say. Okay, then this ammonia we are taking to which temperature in the sense 347 degrees Celsius. 347 degrees Celsius. Okay. Now we will take this ammonia to 347 degrees Celsius while it attains equilibrium because of this reaction, because of like this reaction. Okay. So now this ammonia is taken to 347 degrees Celsius. Okay. It is taken to 347 degrees Celsius while it is at equilibrium. Okay. So ammonia gives N2 gas plus 3H2 gas. Okay. So we have taken ammonia initially. This ammonia is dissociating. We have taken ammonia only initially. We have not taken N2 and H2. This ammonia is dissociated. Therefore, this ammonia comes to equilibrium. At equilibrium, ammonia is present, N2 is present, H2 is present. Okay. Now here given is what in the sense the new pressure here, the new pressure becomes 50 atmosphere at equilibrium. So 50 atmosphere at equilibrium is given. So 50 atmosphere is which pressure? 50 atmosphere we are saying, no, that is which pressure? That is total pressure at equilibrium. Otherwise, pressure of ammonia at equilibrium, what we have to say? They have not mentioned. It is 50 atmosphere is pressure of ammonia at equilibrium is not mentioned. The new pressure becomes 50 atmosphere at equilibrium of the reaction. That means what? Equilibrium mixture pressure is 50 atmosphere. That's what it means. Okay. So equilibrium mixture pressure is 50 atmosphere is given. Okay. So we know that pressure of equilibrium mixture is how much means 50 atmosphere we know. Pressure of equilibrium mixture is 50 atmosphere. That's what it is given. Okay. Next, what they are asking us to find, we'll see. Percentage of mole of ammonia they are asking us to find. Percentage of mole of ammonia decomposed. Percentage of mole of ammonia decomposed they are asking. Okay. So now we have to find what in the sense mole percentage of ammonia decomposed. Mole percentage of ammonia decomposed is equal to what we can write in the sense moles of ammonia decomposed by initial moles of ammonia taken into 100. Okay, it is called mole percentage of ammonia decomposed. Mole percent of ammonia decomposed means how many moles of ammonia decomposed by initial moles of ammonia into 100. So they said like this. Okay, here this shall we say that moles is directly proportional to pressure when temperature is constant and volume is constant. Shall we take like this? In the ideal gas equation, what are the variable terms? Pressure, volume, temperature, number of moles. Let us take volume is constant, temperature is constant, then we can say moles is directly proportional to pressure. Then we can say Then we can say here pressure of ammonia decomposed. Here initial pressure of ammonia we can say, that's all, isn't it? So what we can say in the sense, so we can say that this is directly proportional to, that means this mole percentage decomposed, this mole percentage decomposed equal to so and so, it is directly proportional to what we can say in the sense pressure of ammonia decomposed by initial pressure of ammonia into 100. Sir, initial pressure of ammonia in the sense, shall we take 15 atmosphere? Shall we take this 15 atmosphere as initial pressure of ammonia? What shall we do? Here temperature is constant. Temperature is constant means what? 15 atmosphere is the ammonia pressure when the temperature is 27 degrees Celsius. But ammonia decomposes at which temperature? 347 degrees Celsius. Therefore, temperature is how much? 347 degrees Celsius. After attaining 347 degrees Celsius, temperature should remain constant. Okay. So that initial moles of ammonia, that means initial pressure of ammonia means what? Initial pressure of ammonia when the temperature is 347 degrees Celsius. That is called initial pressure of ammonia. Have we got idea? So initial pressure of ammonia means what? The pressure exerted by ammonia when the temperature is 347 degrees Celsius before decomposition. Okay. That means we want pressure of ammonia. We want pressure of ammonia at 347 degrees Celsius we want before decomposition. Okay. Now here when temperature is 27 degrees Celsius, pressure of ammonia is 15 atmosphere. When temperature is 347 degrees Celsius, what is the pressure? Gay-Lussac law tells what? P1 by T1 is equal to P2 by T2. P1 is how much? 15 atmosphere. T1 is how much? 300 Kelvin. P2 we want. T2 is how much? Convert this 347 into Kelvin. Add 273. Add 273, you will get Kelvin. So how much we are getting in the sense 620 Kelvin we are getting. So T2 we got. Now let us simplify this. Let us simplify this. We will get P2. Okay. This on simplification we are getting P2. That means 31 atmosphere before decomposition. Okay. Understand that before decomposition. Before decomposition. So here what we have done, the pressure of ammonia is 15 atmosphere at 27 degrees Celsius. What is the pressure of ammonia at 347 degrees Celsius? By keeping which and all constant? Number of moles of ammonia is constant, volume is constant. Then only we can take this formula. Okay. So that before decomposition of ammonia I have taken. That means this 31 atmosphere is the initial pressure of ammonia at 347 degrees Celsius. Okay. So 31 atmosphere is the pressure of ammonia at 347 degrees Celsius. At this time, at this pressure, ammonia has not decomposed anything. Okay. Now, at 347 degrees Celsius, on leaving the system, ammonia is decomposing. How much decomposing means X atmosphere is decomposing. Remaining is 31 minus X. 31 minus X atmosphere. We can talk in terms of pressure. Why? Because these are gases. Okay. Because moles is directly proportional to pressure when temperature is constant and volume is constant. Okay. This equilibrium, this process is at same temperature at 347 degrees Celsius only. Therefore, temperature is constant. What about volume in the sense, here you see that they said volume is constant, they said in the sum. Okay. Volume is constant, they said. Therefore, moles is directly proportional to pressure. So, we can talk in terms of pressure. So ammonia is two times ammonia decomposing means one time N2 is appeared. So X atmosphere is decomposing means X by 2 atmosphere of N2 is produced. Okay. Then 3H2. That means 2 ammonia decomposing means 3H2 is producing. So X atmosphere decomposing means how much we will get? 3 by 2 X we will get. Okay. So we got 3 by 2 X. Now we will see the total pressure. We will see this 31 plus X, this 31 minus X plus X by 2 plus 3 by 2 X. 3 by 2 X we have taken. So how much we will get? You see that. Okay. It is 31 minus X. It is a 31 minus x. It is a x by 2. This we are saying x by 2 we are saying. This we are saying that 3 by 2 x. Therefore, how much we will get? What is the total pressure we will get? You see, sir. We will take in another manner also. We can take in another manner how to take in the sense that we will see. Now, better we will take it is 2x atmosphere. If we take 2x atmosphere, 31 minus 2x we can write here. Here we can write x atmosphere, we can write here, we can write 3x atmosphere. Now you see total. What is the total? We will see. Now, if we take total in the sense, now we will see total 31 minus 2x, here x, here 3x. Okay. So we got total. So total is how much in the sense 31 plus 2x, 31 plus 2x. This is the pressure we got. Okay. Which is equal to how much in the sense 50 atmosphere is given. 50 atmosphere is given. Okay. So 31 plus 2x is equal to 50 atmosphere. So from this, what we can find in the sense x we can find. From this we can find it x. If we know x, so we are finding x. This x we know. Then we will go for this one. Moles of ammonia decomposed in the sense that is 2x. That 2x will substitute. Initial moles of ammonia in the sense that is proportional to this 31. That 31 will substitute into 100. X we are getting from this. That x we are substituting. So this on simplification we are getting what in the sense mole percentage of ammonia decomposed, that is so and so. Mole percentage of ammonia decomposed, that we got it. Okay. So here what we have done in the sense moles of ammonia decomposed means that is directly proportional to 2x atmosphere, that we have substituted. Initial moles of ammonia means that is directly proportional to 31 atmosphere, that we have substituted. So we are substituting this x into this one. So we are getting a mole percentage of ammonia decomposed, that is 61.3% we got. Let us go to next sum. Kp for the reaction. Kp for the reaction. N2 plus 3H2 gives N2 plus 3H2 gives 2NH3 is 1.6 into 10 power minus 4 atmosphere power minus 2 is 1.6 into 10 power minus 4 atmosphere minus 2 at 400 degrees Celsius. At 400 degrees Celsius. What will be Kp at 500 degrees Celsius? What will be Kp at 500 degrees Celsius? Heat of reaction of this in this temperature range. Heat of reaction in this temperature is minus 25.14 kilocalories. Okay. Delta H in this temperature is minus 25.14 kilocalories is given. Okay. So now what is the question in the sense Kp is given at 400 degrees Celsius. They are asking Kp at 500 degrees Celsius. That means Kp at different temperatures they are handling. They are handling Kp at different temperatures. They are handling Kp at different temperatures means what is the relation between Kp and temperature we have to see. So what is the relation between Kp and temperature in the sense equilibrium constant is equal to A into e power minus delta H by RT. It is the temperature equilibrium constant relation. This K is called equilibrium constant, delta H is called enthalpy of reaction, T is called temperature. Okay. So now we have to see this relation we have to take. Okay, it is K1 will take, it is T1 will take, delta H remains same at the given temperature range we said. A is constant. Okay, then we will take logarithm on both sides. Ln k1 is equal to ln A minus delta h by r into 1 by t1. Okay, then ln k2 is equal to ln A minus delta h by r into 1 by t2. Okay, then we will take a ln k2 minus ln k1 is equal to what? In the sense ln A get cancelled, therefore minus delta h by r if we take outside, minus delta h by r if we take outside, what we will get? In the sense 1 by t2 minus 1 by t1 we will get 1 by t2 minus 1 by t1. Okay, then ln k2 by k1 we will write it as log k2 by k1, then 2.303 will come. That 2.303 we have to write in the denominator. 2.303 or 1 by t2 minus 1 by t1. Okay, this log means base is 10 here, ln means base is e, base e here base 10 here, therefore 2.303. Okay, sir, now we will substitute the values. Log k2 we want k1 is how much? In the sense 1.6 into 10 to the power of minus 4 atmosphere power minus 2 minus delta h how much given? In the sense minus 25.14 kilocalories, minus 25.14 kilocalories will substitute here. 2.303 r value is how much? In the sense 1.987 into 10 to the power of minus 3 kilocalories per Kelvin per mole, kilocalories per Kelvin per mole. 1 by t2, t2 is how much? In the sense 500 degrees Celsius, convert into Kelvin, 773 Kelvin minus t1, t1 how much? In the sense 400 degrees Celsius, 673 Kelvin. Okay, we have substituted temperature, we have substituted. Now we can simplify this, we can get k2. K2 is called equilibrium constant at 500 degrees Celsius, that is how much? In the sense 1.462 into 10 to the power of minus 5 atmosphere power minus 2. Now we will take next sum. We are taking next sum. The plot of the plot of log kp base 10, log kp base 10 against 1 by t, against 1 by t for the reaction, SO2 gas plus half O2 gas, SO2 gas plus half O2 gas gives SO3 gas, is a straight line with a slope, is a straight line, is a straight line with a slope, is a straight line with a slope 4.95 into 10 power 3, 4.95 into 10 power 3. Calculate kp at 25 degrees Celsius, calculate kp at 25 degrees Celsius. If standard entropies for SO2, O2 and SO3, SO2 gas, O2 gas and SO3 gas are 248.2, 205.1, 205.1 and 256.8, 256.8 joule per Kelvin per mole at 25 degrees Celsius respectively, at 25 degrees Celsius respectively. at 25 degrees Celsius respectively. Okay. So now what is the question? We'll see the plot of log Kp base 10 against 1 by T. So this plot we will see, this plot for this reaction is a straight line, they said. Okay. This plot for this reaction is a straight line having slope this much. So now we will see the graph, we will see, that means what is the relation between Kp and temperature we have to see. So equilibrium constant Kp is equal to A into e power minus delta H by RT. Now we want log Kp, we want, so we will take ln on both sides. Ln Kp is equal to ln A minus delta H by R into 1 by T into 1 by T. Now we will take this ln in the sense base is E, this base E we will convert into base 10. So log to the base 10 Kp is equal to log to the base 10 A minus delta H by 2.303 R into 1 by T. Okay, 1 by T we have taken. Now they said the graph between log Kp and 1 by T is a straight line, therefore it is y. It is plus m x c, y equal to mx plus c we have written here. Y equal to mx plus c, that formula we have written here. Okay, so y is equal to mx plus c, that is called straight line formula we have written. So x is 1 by T, y is log Kp, therefore m is called so and so, m is called this slope. M is we can say this slope we can say, therefore slope is equal to minus delta H by 2.303 R. Slope is equal to minus delta H by 2.303 R we got. Sir. So now we will find delta H from this. So delta H is equal to minus slope into 2.303 into R we have written. Okay. Sorry. So this is equal to minus slope is how much in the sense 4.95 into 10 to the power of 3 given. So 2.303. Now R is how much in the sense 8.314 joule per Kelvin per mole. Okay. R we have substituted. So from this what we can get in the sense delta H we can get. So delta H is how much in the sense minus 9.48 into 10 to the power of 4 joule. Okay. Joule we got. Sorry. So we got delta H value. Delta H value we got here. This slope, what is the unit of slope? What will be the unit of slope that we have to see? Because if you know the slope unit, then only we can cancel. What are the things can be cancelled that we can cancel, then we can get. Slope is dy by dx. That is only no. So dy is which one? Log Kp. Log Kp in the sense for that equilibrium constant in the sense no unit we will take, and 1 by T in the sense 1 by T in the sense Kelvin per Kelvin we can say. So dy by dx in the sense per Kelvin is there. Okay, per Kelvin is there means that delta H. Slope means this one only slope, no. This slope unit will see. Slope means dy by dx. Dy in the sense log Kp, no unit. Dx in the sense 1 by T. 1 by T in the sense Kelvin inverse. Therefore slope is Kelvin. Okay, so slope unit is what in the sense Kelvin. This Kelvin and this per Kelvin get cancelled. Therefore what is the unit for delta H in the sense joule per mole? Joule per mole is the unit of delta H. Okay, we got delta H, we got. Okay, from this straight line we got this delta H. Okay, what they're asking us to find, calculate Kp at 25 degrees Celsius. So we want Kp at 25 degrees Celsius we want. Okay, so we want Kp at 25 degrees Celsius. How to find Kp in the sense, okay, temperature in the sense this is delta H, we know delta H, we know temperature. So Kp we have to find, that means we want A. This frequency factor A we want in order to find Kp. Okay, set. Now what is given in the sense if S naught standard entropies given, standard entropies of SO2, O2 and SO3 given. From standard entropies, we can find delta S naught. Standard entropy of reaction, we can find it. Okay, so we know delta S naught, we have found from this. Delta H naught we have found from this. We got here. We know temperature. From this, what we can find in the sense delta